Welcome to this video lecture. In this lecture, we will exercise solving some problems for calculating the bandwidth of exponential modulated signals. In our first example, we will see how to calculate the bandwidth of an exponential modulated signal where time domain expression of the modulated signal is available. While in our second example, we will see both frequency and phase modulated signals where time domain plot of the information signal is available. So let's start the discussion with our first example. In this example, we are given an exponential modulated signal and we are required to find the average power of this signal, peak frequency deviation being experienced in this exponential modulated signal, peak phase shift which is being experienced in this exponential modulated signal, bandwidth of this exponential modulated signal. So let's start with the first part, that is finding the average power of this sinusoid, that is exponential modulated signal. As we know that sinusoids are power signals and we derived a formula to find the power of such sinusoids or any periodic signals, that is obtaining the magnitude of the given signal and then taking its square and then integrating it over one cycle and averaging it over the time for which it is being integrated. We also discussed that the average power of sinusoid signals can be represented after substituting through this formula. The average power of sinusoids is equal to the square of the peak amplitude of the sinusoid divided by 2. So by using this relationship, we can obtain the average power of this signal, that is 10 square divided by 2, which will be equal to 50. In the second part, we are required to find the peak frequency deviation that is being experienced in this signal. So the peak frequency deviation was represented by delta f, and for the case of frequency and phase modulated signals, we derived the equation of delta f, which was for the case of frequency modulated signals as equal to kf multiplied by the peak amplitude of information signal divided by 2 pi. While for the case of phase modulation, the peak frequency deviation was represented by kp, the constant scaling factor, multiplied by the peak amplitude of the derivative of information signal divided by 2 pi. However, in this given exponential modulated signal, as we are not clear that if it is a frequency modulated signal or a phase modulated signal or some other type of exponential modulated signal. So we need to derive a new relationship for obtaining the peak frequency deviations for such signals where the expression of the exponential modulated signal is given. As we are aware that the derivative of instantaneous phase of a certain signal with respect to time represents the instantaneous frequency of that signal, while the integral of the instantaneous frequency with respect to time represents the instantaneous phase. So for this signal, the instantaneous phase is equal to this part which is being represented in this equation here. So if we take the derivative of the instantaneous phase that was represented by theta of t, we can obtain instantaneous frequency. While if we subtract the central frequency from the instantaneous frequency, that was the carrier frequency omega c, we can obtain the shifts being experienced in the frequency. And if we take the peak value of this shift in frequencies, then that will be the peak frequency shift. And if we divide it by 2 pi, we can convert it to hertz from radians per second. So that will represent the peak frequency deviation being experienced by this exponential modulated signal. So as first part, if we take the derivative of the instantaneous phase to obtain the instantaneous frequency, in this the derivative of the first part will be equal to omega c, while the derivative of this second part of this instantaneous phase, we will get 5 into the derivative of the angle of this signal, that is equal to 3000 t, which will be equal to 3000 multiplied by the derivative of sine of that angle, which is equal to cos of the angle. Similarly, we have another sine wave here where 10 is its peak amplitude, which is a constant number, it will remain as it is, while the derivative of sine of theta is equal to cos of theta into the derivative of theta. So from the derivative of this angle 2000 pi t, we will get 2000 pi into cos of 2000 pi t. In this instantaneous frequency, we have a certain central frequency omega c, that was the carrier frequency, and this part of the expression is representing any shifts which are being experienced in the central frequency, or this second part is causing shifts in the central frequency. So if we subtract omega c, the central frequency of the signal, from this expression, we will be left with the expression that will represent only the shifts which are being experienced in the frequency. Therefore, omega I minus omega c, representing the shifts being experienced in the instantaneous frequency of this exponential modulated signal, which is equal to 15,000 cos of 3000 t plus 20,000 pi cos of 2000 pi t. While if we take as next step the peak value of this signal, that is the maximum value of the shift, we can obtain the peak frequency shifts which are being experienced in this signal. And if we divide it by 2 pi, then we can obtain the peak frequency deviation which is being experienced in this exponential modulated signal. So to calculate the peak value of this signal, in this signal we have two parts where two sinusoids are being added, while the peak amplitude of both the sinusoids is different from each other and the frequency of both the sinusoids is also different from each other. So if we add any two sinusoids which has different peak amplitude and different frequencies, for example, if the peak amplitude of first signal is A1 while the peak amplitude of second sinusoid is A2, if we add these two signals, then we will get a certain signal which will be the composite form of these two sinusoids. For example, if we obtain such a signal, along the time we may experience a certain time instant where the peak amplitudes of these two sinusoids may get aligned and cause the peak amplitude of this resultant signal that will be equal to the peak amplitude of first sinusoid plus the peak amplitude of second sinusoid. Therefore, the peak value of this composite signal where these two sinusoids are being added will be equal to the addition of the peak amplitudes of these two independent sinusoids. So we can represent that delta f is equal to 1 over 2 pi into the peak value of this part, which is equal to 15,000 plus 20,000 pi, as being the peak amplitudes of these two sinusoids. So we can obtain the peak frequency deviation by performing this mathematical calculation, that will be equal to 12,387.32 Hertz. In the third part, we are required to find the peak phase shift which is being experienced in this exponential modulated signal. So by adopting a similar approach, as this part is representing the instantaneous phase of this signal, while the first omega ct portion of this equation represents the running phase and the following portion represents the shift which is being experienced in the phase of this signal. That is, theta of t is representing the instantaneous phase of this signal. If we subtract the running phase, that is omega ct, from the instantaneous phase, then we will obtain the shift in phase, that is phase shift being experienced by this signal. And by calculating the peak value of this phase shift, we can calculate the peak phase shift being experienced by this signal. That will be equal to theta of t minus omega ct and peak value of this signal as referred by delta theta. So by substituting the equation of theta of t, which was equal to, and if we subtract the running phase, that was minus omega ct, from this portion, that is omega ct being cancelled with this minus omega ct, this remaining portion represents the phase shift being experienced in this signal. So if we compute the maximum value of this signal, that is peak value of this signal, that will be the representation of peak phase shift being experienced by this signal. So again here we have two sinusoids being added to each other which are of different frequencies and of different peak amplitudes. If we add these two sinusoids, the peak amplitude of resultant signal will be equal to the addition of peak amplitudes of these two sinusoids. So the peak phase shift being experienced by this signal is equal to 5 plus 10 radians, that is equal to 15 radians. In the last part, that is to calculate the bandwidth of modulated signal. If you recall, the bandwidth of exponential modulated signals can be calculated by using Carson's rule, which was the bandwidth being equal to 2 times the peak frequency deviation plus 2 times the bandwidth of information signal. We have already computed the peak frequency deviation being experienced in this signal, while we need to find the bandwidth of information signal as first step to obtain the bandwidth of modulated signal. Here we are given with an expression of the exponential modulated signal, a time domain expression, where it may be a frequency modulated signal or it may be a phase modulated signal. If we recall the time domain expression of both frequency and phase modulated signals, where in frequency modulated signal, the integral of information signal was being added in the instantaneous phase, and for the case of phase modulation, information signal in its original form was being added in the instantaneous phase. So by comparing the expression of frequency and phase modulated signal with the expression of this exponential modulated signal, as AC, the peak amplitude is being represented by 10 here, and the running phase omega ct is represented by omega ct in both frequency and phase modulated signals. This concludes that this remaining portion in the expression of this exponential modulated signal represents either the integral of information signal if it is a frequency modulated signal, and if it is a phase modulated signal, then this shift portion represents the information signal in its original form. So for the case if it is a frequency modulated signal, then this part represents the integral of information signal, and for the case if it is a phase modulated signal, then this part represents the information signal in its original form. While we are aware of the fact that if a signal, for example x of t, is fed as input to an integrator operator, and if we are obtaining a signal y of t, for example, if the signal x of t is bandwidth b Hz limited, then after passing it through this integrator, its bandwidth will remain same, as the integrator operator does not affect the bandwidth. If a signal of bandwidth b Hz is being fed as input to this integrator operator, the bandwidth of output signal will also be the same b Hz bandwidth. By considering this, if this portion of the exponential modulated signal is either information signal or it is the integrated version of information signal, the bandwidth of this portion will represent the bandwidth of information signal. Therefore, to calculate the bandwidth of information signal, we can actually calculate the bandwidth of the portion which is causing the shifts in phases in this exponential modulated signal's expression. So to obtain the bandwidth of this part which is causing shifts in phase and frequency of this signal, as information signal is a baseband signal, the highest frequency of such baseband signals represent their bandwidth. So the component which has higher frequency, the frequency of that component will be the bandwidth of information signal. For example, in this case, there are two sinusoids being added. The frequency of one sinusoid is 3000 radians per second, while the frequency of the second sinusoid is 2000 pi. So by comparing the frequency of these two parts, we can write the bandwidth of information signal as equal to 2000 radians per second, and if we divide it by 2 pi, we can obtain the bandwidth of this information signal as equal to 1000 Hz. So by substituting the value of delta f which we calculated in part B, and by substituting the bandwidth of information signal that is equal to 1000 Hz in this expression, we can obtain the bandwidth of modulated signal as equal to 2 times 12,387.32 plus 1000, as 1000 being the bandwidth of information signal. So after doing some mathematical calculations, we can obtain that the bandwidth of this modulated signal is equal to 26,774.65 Hz. That is approximately 26 kilohertz. That is the calculations for the part D of this example. So for example, if we are also required to find the deviation ratio that we represented by beta, which was the ratio between peak frequency shift being experienced by an exponential modulated signal and the bandwidth of information signal that is causing the shifts in the bandwidth of that modulated signal. So for this part E, for example, we are aware that this beta parameter, that is deviation ratio, is equal to the peak frequency deviation of the modulated signal divided by the bandwidth of information signal. If we substitute the value of delta f, that was equal to 12,387.32 divided by 1000, we can obtain the value for this deviation ratio, that is beta, is equal to 12.387. This deviation ratio provides the information about the rate of modulation that is being performed in this exponential modulated signal. That is a comparison of the bandwidth of information signal and the deviation which is being caused in the modulated signal. So in the first part, we were required to find power which is equal to the square of peak amplitude of this information signal. While in the second part, we were required to find peak frequency deviation. So we adopted an approach, we derived a formula that was equal to taking derivative of the instantaneous phase of this signal we can obtain instantaneous frequency, and then subtracting the central frequency from that part, we can obtain the shift which is being experienced in the instantaneous frequency. And by taking the peak value of the shift of frequency, we can obtain the peak frequency shift or the peak frequency deviation that was represented by delta f. Similarly, in part C, we were required to find peak phase shift, where this part is the instantaneous phase. If we subtract the central phase, that is the running phase omega ct, we will get the portion which represents the shifts in phase. And by computing its peak value, that was equal to 5 plus 10, we can obtain the peak phase shift which is being experienced by this signal. For calculating the bandwidth of the modulated signal, we can use Carson's rule, which represents the bandwidth as equal to 2 times the peak frequency deviation plus 2 times the bandwidth of information signal. While to calculate the bandwidth of information signal, this part's bandwidth has a direct representation of the bandwidth of information signal, as this portion will be either information signal itself or it will be the integrated version of information signal. And the integration operation does not affect the bandwidth, so the bandwidth of this part of this exponential modulated signal will be the bandwidth of information signal. As the information signal is a baseband signal, so the component which has a higher frequency or the maximum frequency of this portion will be equal to the bandwidth of this signal. So by computing the bandwidth of information signal and by using the peak frequency deviation, we can calculate the bandwidth of modulated signal. Similarly, the deviation ratio that was equal to the ratio between peak frequency shift and the bandwidth of information signal can also be obtained in this example. Example number 2. In this example, we are required to estimate the bandwidth of frequency and phase modulated signals for the case when information signal is represented by this triangular signal, that is m of t, where the constants, the scaling factors for the case of frequency modulation and phase modulation are given as kf and kp. So let's start by estimating if a frequency modulation is performed for the case that information signal is represented by this triangular wave. According to Carson's rule, bandwidth of a frequency modulated signal can be represented as 2 times the peak frequency deviation plus 2 times the bandwidth of information signal. And we are aware that delta f, which is the peak frequency deviation, is represented by kf multiplied by the peak amplitude of information signal divided by 2 pi for the case of frequency modulated signals. So in order to obtain the peak frequency deviation for the case of frequency modulated signals, we require the value of kf, which is provided as 2 pi into 10 raised to the power 5 in this example, and we require the peak amplitude of information signal, that is unity plus 1 and minus 1 for this example information signal. That is, we are given with delta f equals to 2 pi into 10 raised to the power 5, and we have the peak amplitude of information signal equal to 1. So by substituting the value of these two parameters in this expression, we can obtain that delta f is equal to, that is 1 into 10 raised to the power 5 hertz as peak frequency deviation if frequency modulation is performed by considering this m of t as the information signal. The second parameter which is required to calculate the bandwidth of this modulated signal is the bandwidth of information signal, where the information signal is m of t and this example information signal is a triangular wave. So to determine the bandwidth of m of t, as this information signal is a periodic signal and it is a triangular wave, we can apply Fourier series expansion. We can compute the power of its harmonics. That is, m of t can be represented as m of t signal with summation of n sinusoids, where the peak amplitude of every sinusoid is different and the frequency of each sinusoid is also different to each other. Therefore, we can represent its frequency domain representation by a discrete finite number of harmonics, where omega naught represents the fundamental frequency of this signal. As the time period of this triangular wave is given as 2 into 10 raised to the power minus 4 seconds. So from this we can compute the fundamental frequency of this sinusoid, that is omega naught. That is, omega naught equals to 2 pi f naught, where f naught is equal to 1 over t, while t represents the time period of this signal, that is equal to 2 into 10 raised to the power minus 4 seconds, which can be expressed as 10 raised to the power 4 pi radians per second. So as exercise, you may perform the Fourier series expansion of this triangular wave, as we have also thoroughly studied these aspects in chapter number 3 of this course. As for such triangular waves, only odd harmonics exist. That is Cn, the peak amplitude of these sinusoids, can be expressed as 8 divided by pi square n square, while if n is an odd number. And for the harmonics with index n as even numbers, such triangular waves don't constitute any power. So only odd harmonics exist in such signals. While with an increase in the value of the index of harmonics, that is n, a rapid decrease in the power of these sinusoids can be observed here. That is, for n is equal to 1, we have Cn equal to a sufficiently large number, while if we increase the value of n here, for example 3, then the square of 3 is equal to 9, and 8 divided by 9 is a smaller number. Further, by increasing the value of n to, for example, n is equal to 5, the power, the peak amplitude which represents the power of this sinusoid for a certain index of harmonics, can be observed as rapidly decreasing with an increase in n. So by conducting a simple analysis, we can calculate that the third harmonic contains only 11% of the fundamental frequency, and the fifth harmonic occupies only 4% of the fundamental frequency. That is, the third and fifth harmonic only occupy 1.21% and 0.16% of the total power. So for calculating the bandwidth of information signal, we have a certain frequency that we referred as fundamental frequency, and 3 times of this fundamental frequency is 3 omega naught, and 5 times of this fundamental frequency represents a certain frequency which is 5 omega naught. And we have observed that the bandwidth of this signal is very rapidly decreasing with an increase in the index of these harmonics. The accurate bandwidth of this information signal may be very large, while most of the energy is concentrated up to its third harmonic. We are justified in assuming the essential bandwidth of information signal m of t, which is a triangular wave here, as the frequency of third harmonic, that is 3 into 10 raised to the power 4 pi, where omega naught was 10 raised to the power 4 pi radians per second. So we can convert it to hertz. That is, the frequency of third harmonic being 3 times the fundamental frequency equals to 3 into 10 raised to the power 4 divided by 2 pi, which can be calculated as 1.5 into 10 raised to the power 4 hertz, which can be referred as 15 kilohertz. So as most of the energy is concentrated in the band from 0 frequency to the third harmonic of this signal, for this case of information signal being a triangular wave, therefore we can calculate the bandwidth of information signal as equal to 15 kilohertz. So by using the bandwidth of information signal which we have computed here, and the peak frequency deviation of frequency modulated signal which we have computed here, in the equation number 1, that was the Carson's rule, we can obtain the bandwidth of frequency modulated signal. That is, bandwidth is equal to twice the peak frequency deviation plus bandwidth of information signal. By substituting the values, as delta f is equal to 1 into 10 raised to the power 5 hertz plus the bandwidth of information signal is equal to 15 into 10 raised to the power 3 hertz, we can calculate the bandwidth of frequency modulated signal as equal to 230 kilohertz. We also rearrange the formula for the bandwidth of such exponential modulated signals in terms of the bandwidth of information signal and the deviation ratio that we represented by beta. This is also the Carson's rules representation in terms of deviation ratio. So if we calculate the deviation ratio beta, that was equal to the ratio between peak frequency deviation and the bandwidth of information signal, which can be referred as 6.66 approximately 7. So by substituting the value of beta and the value of bandwidth of information signal in this expression, we can obtain that 2 times the bandwidth of information signal multiplied by 6.667 as the value for deviation ratio plus 1, which is again 230 kilohertz. So similarly, for the case of phase modulation, as we know that the peak frequency deviation for the case of phase modulation is represented by Kp into the peak amplitude of derivative of information signal divided by 2 pi. We have information signal available here. If we take the derivative of this signal and obtain the derivative signal of information signal, in time domain it will be equal to m dot of t. While as we know that these are straight lines, the slope for each straight line can be calculated. So if we calculate the slope of first increasing line, that is from -1 to +1, between the time instances, for example, if we refer them as t0 up to the time instant t1, the slope can be computed as the value of information signal at time instant t1 minus the value of information signal at time instant t0 divided by the separation span between these two time intervals, that is equal to t1 minus t0. So by substituting the values, we can get that as the amplitude at time instant t1 is equal to +1 minus the amplitude at time instant t0 is equal to -1 divided by, as the time separation between two consecutive peaks is represented by 2 into 10 raised to the power -4 seconds. Therefore, the interval from t0 to t1 represents only half of that time period, that is half of the time period t of this wave, while t was represented as 2 into 10 raised to the power -4 seconds. So the separation span between these 2 points is equal to, that is 1 into 10 raised to the power -4 seconds. So we can represent the slope of the straight line from time interval t0 to the time instant t1 as equal to 2 into 10 raised to the power 4. So from time intervals t0 up to time interval t1, we have a straight line which will have a constant slope, which we have calculated as equal to 20,000. Similarly, we have another straight line from time interval t1 to time interval, for example t2 here, which has a negative slope while the slope is exactly same. So we will have a constant slope from time instance t0 to the time instant t2, while being a decreasing line, its slope is equal to, for this span, -20,000. Similarly, from time instant t2 to time instant t3, we again has an increasing line, so it will represent a positive slope. And from time instant t3 to t4, again we have a decreasing line, which will be represented by a negative slope, and so on. So this signal, this square wave, represents the derivative signal of this triangular information signal. From this, we can see that the peak amplitude of the derivative of information signal is equal to 20,000 for this example case, which can be represented as mp dot, which was the peak amplitude of the derivative of information signal, as equal to 20,000. As this linearly increasing straight line has a positive slope and its slope is computed as +20,000, while this decreasing line has a negative slope which we computed as equal to -20,000. The slope of the line for within each these spans is constant, therefore we obtained a square wave, and so on. For the span from t2 to t3, we have again an increasing line where its slope can be calculated as 20,000 +20,000, and so on. So from these calculations, we have obtained the peak amplitude of the derivative of information signal, which is equal to 20,000, by substituting this peak amplitude of the derivative of information signal in this expression for the peak frequency deviation, and by substituting the value of kp, the constant scaling factor, which was given in the question as equal to 5 pi in this expression, we can calculate peak frequency deviation as equal to 5 pi multiplied by 20,000 divided by 2 pi, which is equal to 50 kilohertz. The formula for calculating the peak frequency deviation for both frequency and phase modulation signals is different, as frequencies are influenced by the derivative signal in phase modulated signals, and frequencies are influenced by the information signal itself for the case of frequency modulated signals, whereas the bandwidth can be calculated for both the cases with the same Carson's rule, that was equal to 2 times the peak frequency deviation plus the bandwidth of information signal. So by substituting the value of delta f in this expression, that we have calculated as 50 kilohertz plus the bandwidth of information signal, which is 15 kilohertz, the bandwidth of phase modulated signal can be thus calculated as 130 kilohertz. So in this example, an information signal was given and the scaling constant factors for frequency and phase modulations were given, and we were required to obtain the bandwidth of frequency and phase modulated signals. In frequency modulated signals, frequencies are directly influenced by the amplitude of information signal, therefore the peak frequency deviation can be calculated, while in the case of phase modulation, the peak frequency deviation can be calculated from the derivative of information signal. Therefore, we have obtained the derivative of this information signal as this square wave that was m dot of t. So after calculating peak frequency deviations experienced for both frequency and phase modulated signals, the other part which we required in the Carson's rule, that was the bandwidth of information signal, where information signal is this triangular wave. As this triangular wave is a periodic signal, Fourier series expansion can be applied, and we know that only odd harmonics exist in this function, where by conducting some analysis we obtained that most of the power of this signal lies up to the third harmonic, that was 3 times the fundamental frequency of this signal. So from this analysis we calculated the bandwidth of information signal as equal to 15 kilohertz, and therefore the bandwidth of both frequency and phase modulated signals as equal to 230 kHz and 130 kHz respectively. While it can be observed that by substituting some other value of these constants Kp and Kf, delta f, the value of peak frequency deviation, that is delta f, can be manipulated and bandwidth can be manipulated. Therefore, these constant parameters Kp and Kf are critical while designing such frequency and phase modulated signals. Thank you for attending this lecture. If you have any question, you can write it to me through email, or you can ask it during our upcoming online session.